In all of the models that we've built so far, we've known the intercept. That is, we've known the starting value of our dependent variable, the starting value of the output. Sometimes we come in after the start and we don't know the starting value of the output. Instead, we know the rate of change and we know some current state of the model. In other words, sometimes we know the slope, but instead of knowing the intercept, we know a pair of values, an x value and the corresponding y value. In that case, we can use this alternate form of the equation for a line to write down an equation that describes our model. This form still includes the slope, but instead of using the intercept, we say we're going to subtract our given values from the x and y variables in our equation. Why does this work? Well, remember the slope is the change in y divided by the change in x. So putting that another way, in terms of multiplication instead of in terms of division, we can say that the change in y is going to be equal to the slope multiplied by the change in x. But then that's just what this form is. We know that the slope in a linear model is the same for any pair. So this works for thinking that the change in y is any arbitrary value of y minus the known value of y. And the change in x is similarly any arbitrary x minus our known value of x. So once we've substituted in then our known value of x, our known value of y, and our known slope, we have now a linear equation in two variables, and we can do a little bit of algebra to isolate the value of y and to get an equation in the nice form, the slope-intercept form, y equals mx plus b. Okay, so how do we do this? In this example, we're told that we want a line with slope 3/5, and we want it to pass through the point x is -10 and y is 4. And we're going to use the point slope form. So y minus the given y is equal to the slope times x minus the given x. So plugging into this form, we have y minus the given y is 4 equals our slope 3/5 times x minus the given x is -10. And so that's the equation for our line. If we just want any old equation for this, we're done. We now have an equation describing the relationship between x and y. Of course, it's not a very nice equation. In particular, it's not an equation that lends itself to writing function notation. And also, if someone else comes along with a different point and writes a different point slope equation, we can't know for sure whether or not they're describing the same line. So if we want to work with this anymore, it's useful now to get this into slope-intercept form. And now, the big picture to get this into slope-intercept form is we just need to isolate y. But that's always going to follow the same steps for any slope-intercept form. So I'm going to write out the steps here. Our first step is if when we plugged into the form, there was anywhere we got minus a negative, we're going to rewrite that as plus a positive. So in this example, that needs to happen here. So our equation is going to become y minus 4 equals 3/5 times, in parentheses, x, instead of minus -10, we'll have x plus 10. So that was the first step. And this is already simpler than what we had a minute ago, because instead of that minus a negative, we're going to have plus a positive. Our second step is to distribute on the right to get rid of the parentheses. So the left side, we're still not doing anything. We're just going to keep y minus 4. On the right, we're distributing the 3/5. So we'll have 3/5 times x plus 3/5 times 10. Now, when you use the distributive property, you don't necessarily have to write down the multiplication at this stage, but I want to use a calculator to do 3/5 times 10. So I'm going to write down that multiplication. And then I'm going to actually do the multiplication. And now I have the equation y minus 4 equals 3/5 x plus 3/5 times 10 is 6. Okay, so now we have no minus a negative, and we have no parentheses, and we've worked out all the multiplication on the right. The last step is to add or subtract a number to get y alone. So right now what's happening to y is that 4 is being subtracted from it. So I'm going to add 4 on both sides. On the left, -4 plus 4 cancels out, and we're just left with y. On the right, we have 3/5 x plus 6 plus 4 is 10. So our equation then is y equals 3/5 x plus 10. And of course we can check this. What we need to check is that our given point really is on this line. So we need to check that 4 really does equal 3/5 times -10 plus 10. And putting this right-hand side into the calculator, we see that that really does come out to 4. So this equation really is correct. Okay, so the point-slope form gives us a really direct, straightforward way of getting the equation given the slope and a point. There is an alternate method. If you'd rather, we can write down the slope-intercept form, plug in the given point, and use algebra to find the value of b. So in this method, we have y equals mx plus b, and we're going to plug in our known slope for m, our known x value for x, and our known y value for y. So we're going to plug in m is 3/5, x is -10, and y is 4. So our equation becomes 4 equals 3/5 times -10 plus b. And now we just need to solve for b. So we'll multiply -3/5 times 10. We'll get 4 equals -6 plus b. And now we want to eliminate the -6, so we'll add 6 on both sides. And we'll get that b is 10. And so our equation again is y equals 3/5 x plus 10. Especially when we have relatively unpleasant numbers, the point-slope form has two big advantages. The first is that we get an equation right away. If we just want to do something very simple, we can just use the point-slope version of the equation just right away without needing to get to the slope-intercept form. Second is that there's just less thinking involved. There's less decision-making involved in going from the point-slope form to the slope-intercept form than there is in solving for b. However, you can use whichever method you like better. For the rest of our examples here, I'm going to continue to use the point-slope form, and you should practice using the point-slope form a few times in the homework. If at that point you decide you like solving for b better, that's fine, you can do that. So let's see another example. In this example, we are told that the price of an object was $9 in 2002 and $15 in 2005. We're going to assume that the price has been increasing at a constant rate since the object was released in 2000. Our variables are going to be x, the number of years since 2000, and y, the price in dollars of the object. Now, the first question we should ask is how we know that this is actually a job for a linear model. And in this case, we know that this is a job for a linear model because we are told that the price is increasing at a constant rate. So the specific phrase that tells us is that phrase, constant rate. Whenever we know that the output is changing at a constant rate, we know that this is a job for a linear model. Okay, now in this story we were not told the slope, but what we were told was two pairs of values. I'm going to make a little table here to help us organize our information. So we are told information about a year, which is related to the value of x. And we're told information about the value of y. So we are told that in the year 2002, the price is $9, and that in the year 2005, the price is $15. So 2002 and 2005 are not directly the value of x. Instead, we want the number of years since 2000. So to find the first value of x, we'll take 2002 minus 2000, which is 2. When x is 2, y is 9. For the second given year, we'll take 2005 minus 2000, which is 5. So when x is 5, y is 15. The two pairs that we were given are the pairs 2, 9, and 5, 15. And again, the reason that we were subtracting 2000 specifically is because our x value represents the years since 2000. Okay, so how can we use that information to determine the slope then? We know that the slope is the change in y over the change in x. So we can do this subtraction in the table if we want. We go from 9 to 15. The change in y is going to be 15 minus 9. And then for x, we go from 2 to 5. So the change is going to be 5 minus 2. Okay, and now we can work this out. 15 minus 9 is 6. 5 minus 2 is 3. Our slope is 6 divided by 3, which is 2. Now, our slope, the numerical value is 2. In the context of the problem, the units are the units of y, which is dollars, per, and then the units of x. X is in years, so per year. Units of y per units of x, dollars per year. And what does our slope mean? Well, it's the rate of change. So the price has been increasing by, we'll use the numeric value of the slope, and then we'll give it the units dollars per year. The price has been increasing at a rate of $2 per year. Okay, so now we know the slope. The slope is 2. Notice that our x values, neither one of them is 0. So we don't know the value of y when x is 0. That's our cue to use the point slope form. And we can use whichever pair we want. The point slope form, remember, is y minus the given y equals the slope times x minus the given x. I'm going to choose to use the given x, y pair 2, 9. By default, I'm going to choose the point with the smaller x value because that means I get to do arithmetic to smaller numbers. It doesn't matter which of our 2 points we choose at this step, as long as we use the same one through the whole step. Okay, so first we're going to write down the equation. Y minus our given y is 9 equals our slope times x minus our given x is 2. Our first step is to rewrite any minus and negative as plus a positive instead, but we don't have anything to do for that. Our second step is to distribute on the right, so that'll give us y minus 9 is 2x minus 2 times 2 is 4. Our third step is to take that equation, y minus 9 is 2x minus 4, and add or subtract to get y by itself. We have a 9 subtracted from y. We want to get rid of that, so we're going to add 9 on both sides. On the left, minus 9 and plus 9 cancel out, and we just have y. On the right, we have 2x plus negative 4 plus positive 9 is positive 5. That's our equation. Now, how could I check that this is the right equation? Well, to know that this is the right equation, I need to know that 2, 9 is a solution. So that 9 is equal to 2 times 2 plus 5. Well, 2 times 2 is 4, plus 5 is 9. And I need to check that 5, 15 works. So that 15 is equal to 2 times 5 plus 5. Well, 2 times 5 is 10, plus 5 really is 15. So that also works. So if we were given 2 points, in order to check, we just check that both of our pairs are in fact a solution to the equation. Remember, it only takes 2 points to fix a line. So if both of our points work in this equation really is describing the right line. The last question we're going to ask in this example is, what does the value of b mean? Right, we got the y equals mx plus b form. So now we know that b equals 5. What does that mean in this equation? Right? Recall that b is the value of y when x is 0. In this example, x equals 0 means, remember, x represents the number of years since 2000. So x equals 0 means the year 2000, which is when the object was released. So when x is 0, so in the year 2000, y represents the price of the object. So the price of the object was the value of b, so was $5. So when we use the point-slope form to get the slope-intercept form, we can still interpret the intercept in the equation we end up with, just the way that we've interpreted the intercept all along. So getting that slope-intercept form is actually giving us new information. Just to practice using the point-slope form, we're going to see a couple more examples. So these two examples, we don't have any situation. We're just using raw numbers. So we're given the points 2.8, 8.04, and 5.2, 13.56. So I think the easiest way to look at this is to put these into a little table. So when x is 2.8, y is 8.04. When x is 5.2, y is 13.56. We can say the change in y is 13.56 minus 8.04, which is absolutely a job for a calculator. It's going to be 5.52. The change in x is 5.2 minus 2.8, also a job for a calculator. That's going to be 2.4. The slope, then, is the change in y over the change in x. The change in y, we said in the table, was 5.52. The change in x, we said, was 2.4. And so our slope, doing that division, is 2.3. Now we can put that into the point-slope form. So the point-slope form is y minus the given y is equal to the slope times x minus the given x. And I'm going to use the slope is 2.3. We just found that. I'm going to choose our first point for the given point. So the given x is 2.8. The given y is 8.04. We'll have y minus 8.04 equals 2.3 times x minus 2.8. We don't have anywhere that we've written minus a negative, so we'll start with step 2, which is to distribute. So y minus 8.04 equals 2.3x minus 2.3 times 2.8. Y minus 8.04 equals 2.3x minus, and that second multiplication, of course, is a job for a calculator. We get 6.44. Finally, we're going to add on both sides to get y by itself. So we have y minus 8.04. We'll add 8.04 on the left and also on the right. On the left, minus 8.04 and plus 8.04 cancel out. So we'll just have y equals 2.3x plus negative 6.44 plus 8.04 on a calculator works out to 1.6. So this is our equation. And I'm not going to check this here because the next step has us checking. So in this next step, we're given x is 2.8 and y is 8.04. And we want to confirm that 8.04 is equal to 2.3 times 2.8 plus 1.6. And this is something we're just going to throw into the calculator. We'll take 2.3 times 2.8 plus 1.6. And that really does work out to 8.04, which is what we wanted to see. Similarly, next we're given x is 5.2, y is 13.56, and so we hope to see that 13.56 is equal to 2.3 times 5.2 plus 1.6. And so again, on the calculator, we'll say 2.3 times 5.2 plus 1.6. And that really does work out to 13.56. And so just punching these into the calculator, we see that this checks out. Okay, let's see one more example. In this example, we're told that the output is 55.76 when the input is 1.2. And then y decreases by 3.2 each time x increases by 1. So again, I'm going to organize this given information into a little table. I'm told that when x is 1.2, y is 55.76. And then I'm told that y decreases by 3.2 each time x increases by 1. So when x has gone up to 2.2, y will have gone down to 55.76 minus 3.2, which is 52.56. And of course, that subtraction is a job for the calculator. Our slope is the change in y over the change in x, which is negative 3.2 over 1, based on what we wrote in the table. So just negative 3.2. There are other ways we could organize this. We could even spot that really this problem is directly telling us that the slope is negative 3.2. But if we make a habit of just sort of sketching a little table at the beginning, it kind of makes it a little bit easier to keep track of what we're doing. So now we can write the equation that models this situation. We'll start with y minus our given y is equal to our slope we just found, negative 3.2, times x minus our given x. We don't have any plus a negative, so our next step, we're going to distribute y minus 55.76 equals negative 3.2x minus negative 3.2 times 1.2. Now we're going to have a minus a negative. We're going to have y minus 55.76 equals negative 3.2x plus, because it's minus a negative, and we'll do 3.2 times 1.2. So we get 3.84. Okay, last step. We're going to add 55.76 on both sides to get y by itself. And we'll have y equals negative 3.2x plus 59.6. And this is our equation. So that's the point-slope form. We'll use it whenever we can find the rate of change. We know we want a linear model, but none of the output values we're given is the starting value. That is, we don't know the value of y when x is 0.